warahmatullahi wabarakatuh. Today we will be discussing the we are towards the end of this course. We are going to discuss today basic control architecture in mechatronics system. The topics that we will be covering is mostly distributed control system, SCADA control system. SCADA stands for Supervisory Control and Data Acquisition System. And then we will be discussing IIoT based SCADA and uh, digital twin, and then we will conclude with the comparison between Industrial Revolution 4.0 versus Industrial Revolution 5.0. So without further ado, let's begin, inshallah. So before we go into the distributed control system, let us discuss briefly what control is all about. Control consists of monitoring state of a critical parameter uh, and detecting when it varies from the desired state, desired value, and taking action to restore it. So basically in control, you have a sensor that measures the critical parameter, and then you compare it with the set value, and then based on the error, you take some action, which is the controller, on the actuator that actually converts your control into an uh, action state. So in control can be majorly categorized into discrete control and um, continuous control. Discrete control deals with a system in which each element can only exist in a certain defined state. Basically, it is on-off control. So you either on state or off state. One example is this industrial fan. So you measure the temperature based on this temperature set value. You compare the set value. If it is below the higher than the set value, then you start this fan through this logic control system. So this is the controller, and this is the motor is the actuator. So you control this motor starter, you turn it on and off, so the motor becomes on and off. So this control logic can be implemented via programmable logic controller, PLC, as we have shown earlier in our PLC lecture, that you can convert any logic gate system into a PLC program. On the other hand, analog control deals with a system where the variables can be continuously measured and you give a continuous control action, not just on-off control. One example is a driver is trying to control his steering system to maintain the car into a straight path. So basically, your eye, driver's vision is acting as a sensor, and there's a set point that it is a straight path. If there is any deviation, driver will control the steering to maintain this automobile into a straight path. So if you have an autonomous system, then this driver's vision will be replaced with a um, vision system, machine vision system. Okay. So in continuous control or analog control, you have either proportional controller where you have a simple op-amp circuit, you have a set value and you have a desired value. You convert them into a voltage and then you compare it. And the differential voltage will be magnified with a simple proportional controller through an op-amp circuit, which we have seen in our in using non-inverting amplifier, which you can do it using the lectures which we have where we have discussed the various op-amp circuit. On the other hand, the problem with the pure proportional controller is that it will have a steady state error, and that usually will not be able to overcome using only proportional controller. However, if you use an integral value integration of the proportional, means you are multiplying the error with an control parameter, where in integral circuit or proportional integral controller you are integrating over time using an op-amp circuit to integrate this error value over time, so that throughout the time you integrate, and after certain time you will have certain uh, value that will help you to overcome this steady state error. And derivative controller is used to make sure your response to be fast, or if you did it basically dictates how fast you want to have the response if there's any change in the state set parameter. Control system architecture can range from simple local control to highly redundant distributed control system. So local control means your controller is attached with all the sensor and actuators and operator interface are all locally means within a very short range. All these things are connected, and then you bring these you only from your operator station. You just start stop the system. You change the set point, and you can monitor some alarm or status condition. Now, on the other hand, if you have a centralized control, then your controller is brought into the control room. You have many stations and you don't have any controller here. You can see you have sensors and actuators, no controller here. So this is highly centralized control system. On the other hand, in distributed control, you have controller in every stations. It is distributed, and all the station various status value or some uh, extraordinary control can be brought into the controller stations. You can have a redundant controller in the controller stations as well. So example is here. You have the controller and you have the station, sensors, actuators, you have a process, and you have another control station here. You have another control, three control stations, all are connected through network cable to this central control uh, room where you have another redundant control. If necessary, you can intervene this controller, you can override this controller. So this is the important aspect of distributed control. In the case of distributed control, it is this control room is not very far away from the all the control station. It is within. It's not like in a different city or in a different country. This control room. It is within the same premises maybe or different premises, and these are in the shop floor. There is another similar concept available in Scada, where Scada stands for supervisory control and data acquisition. So these SCADA systems, there are a little bit overlap. Sometimes you can find that it is overlapping with DCS, but there is a very distinct differences between the SCADA and DCS. Um, DCS is very much process oriented. They are not bothered about long time data acquisition and data gathering, whereas on the other hand, SCADA is very much data gathering oriented. When you say you want to see a 5 years data should be stored for different stations, and you want to monitor this data and you want to analyze this data for prediction of the trend and all sort of things. So this is we call SCADA system. Examples can be given here. In SCADA, water distribution and wastewater collection system. So these can be in different cities. You can have water distribution system and wastewater collection system. So it is in a different geographical location. Whereas DCS is more localized. Water and wastewater treatment could be localized into a single place. Oil and gas pipeline, of course, it will cross or it will be across the geographical region, different cities, different countries, whereas oil and gas refineries are more localized. So SCADA and DCS, the main difference, one of the major differences, SCADA take care of large geographical region, whereas DCS is more like localized control, localized place you will apply DCS system. So this is an example of an SCADA system. It is called a star connection. So you have a central control station, you have a data historian, which is basically a database that captures all the station data for various parameters for a long time, maybe 5 years, 10 years. Now this SCADA is now people are going into iSCADA or eSCADA, internet-based SCADA system using cloud storage, which we will discuss later on, inshallah. This is a ring topology. This is also a SCADA system, but it is a different topology. And this is a DCS system where you have a more like LAN-based infrastructure, whereas in SCADA it is not LAN, it is WAN, wide area network-based infrastructure. And this is more localized. Uh, all these control room are locally installed. So now people are bringing SCADA into to internet-based SCADA or a cloud-based system. We using MQTT protocol, which we will show you later on. MQTT stands for Message Queuing and Telemetry Transport, which we will see in next few slides, inshallah. So in our laboratory, we have implemented a demo unit for implementation of IoT-based SCADA system for teaching and learning purpose in our laboratory at International Islamic University, Malaysia. My student Muhammad Banawir helped me in this project. He was my final year project student. So we have an existing PLC system. This is our PLC system, and a pneumatic system. This is a pneumatic trainer. So what we wanted to simulate is that uh, let me go forward a little bit. We wanted to simulate this pneumatic cylinder will reciprocate to test a recliner chair. That is what we wanted to simulate. So this is a real life application, but we wanted to simulate this real life application. So what we did is basically we connected this computer with through this LAN infrastructure with these two PLCs. These PLCs have their own MAC address, and we connected so I can now access through this LAN infrastructure any PLC. Data can be transferred and command can be transferred to the PLC. Data can be transferred from the PLC as well. So then what we did is basically we developed a Node-RED, is an open source software. Using the Node-RED, we developed a GUI to monitor these PLCs. On the left-hand side, we have one PLC. On the right-hand side, we have another PLC, and we develop a GUI to see how many reciprocation cycle has been completed. And all these data were coming through this LAN router to this computer, and this computer is hosting this Node-RED GUI, graphical user interface. Here we are showing 4 PLC, but actually we in real life we use 2 PLCs. And then we use our phone to have to install an app, a free app. No, it's not purely free. We have to pay for this. A remote read, which is corresponding Node-RED GUI, which can be shown on this remote read app, and it is real-time updating through this Node-RED. So if this Node-RED computer is connected to the internet, and this is also communicated through internet, so you can look at the same thing from anywhere in the world. So this is a beautiful example of IoT-based integration system. And on top of this, we wanted to store this data for long period of time using a SCADA, cloud-based SCADA system. So we send this data via MQTT protocol to Amazon Web Service. They have their DynamoDB Dynamo database. We store this data there, which we will show also in our demo video. So this is the demo video. Let's have a look at it. Oh, I don't know why. Let's hold on for a while. Um, I don't know why I cannot run this video. Okay, let me see if I can run it from some other place. Let me pause here for a while, then I come back again. Okay, we are back again. So I restored the video. Let me play the video. So here I'm starting the first PLC to reciprocate this pneumatic cylinder. And this is the second one. I'm turning it on. So it will also start to reciprocate. So now this data is going to via this PLC on this side to this Node-RED GUI. You can see this is increasing. This is also increasing in real time.
Your smartphone, you can monitor that it is going up.
Yeah, you can
go
see
until 13, and this one will go until 30 seconds. It stops.
Okay. Now in the DynamoDB, also you can see it is getting updated. As you can see, the PLC station on the left hand side, PLC station right hand side, it is 44, 57, 44, and with different timestamp. And now if you refresh, you will see it will increase to 50 and 53 at different timestamp. So this is how it will be stored for any period of time, for a long period of time in the DynamoDB, as long as you have to pay for this cloud storage. Okay, let's move on. Okay, now in the next slide, we are going to show how we upgraded and value added to an existing 3-axis CNC machine for teaching and learning purpose. So CNC machine is a technology of the IR 3.0 revolution, Industrial Revolution 3.0. Now we would like to convert it into IoT-based monitoring system for which is compatible for IR 4.0. So basically what we did is this was a modular controller that we have developed using Raspberry Pi to control the CNC machine. We developed a GUI using C Sharp, and then we also connected this machine with mechanical modification, and we did connection of electrical controls with a CNCX Pro controller. So this is the CAD controller case design. And this is a graphical user interface that was developed in-house using C Sharp. It has various features like jog, and then we can upload the program and so on and so forth. And this is where we connected this GUI to AWS, which is Amazon Web Service, via not MQTT protocol, via another protocol called HTTP protocol system. So what this is the infrastructure. So you can run this CNC either by this modular controller, and then you can throw this data from the GUI to via Raspberry Pi to this Amazon Web Service DynamoDB, or you can run it via uh, laptop, and from the laptop you can send this data to AWS. So this is what we have developed. We can run it using this modular controller, and this data is going to that various data is going to this AWS system. And this is how we can show the machine status, alarm, idle, and so on and so forth, different timestamp. We can run it via laptop as well. Okay. Now we are going to discuss another very important concept of IR 4.0, which is called digital twin. We developed in our laboratory this machine we call laser EDM-based hybrid micro machining system, where you can make a small hole using laser, and then you can fine finish using electro discharge machining, which is a sparking. You use a spark to machine the workpiece. And the exact digital version of this machine is shown here. This is we call digital twin. It is fully functional and real time. It can be real time updated the status from this machine via web-based communication. Let me show you a demonstration. So this is the infrastructure where you have this machine connected through Firebase web service to this digital twin. So this is how the digital twin is getting updated by receiving data from this real time from this machine. Also, digital twin can be used to give a feedback to this machine for safety purpose. If there is any collision is detected without having any extra sensor installed, this digital twin can give a feedback to the system, and the machine can be stopped immediately. So this is the video we would like to share with you. So this is the laser. First we do the laser hole, then we do the EDM hole, and then digital twin system for hybrid system. As you can see, if the digital twin moves, the actual system also moves. It's updated real time. And then once the laser is done, then we will do the EDM process. Here you can see both are moving in the real time, same time. So you can do the EDM now. So this EDM is being carried out. And this is as soon as it detects an obstacle, it will stop the machine immediately. You can see here as well, it will be stopped immediately. Yeah. So this is a very interesting topic. And offline also we can do the simulation of the system offline. So this is an example of digital twin system. I think we can skip the remaining. Okay, now we would like to discuss a little bit about the IR 4.0 is already has gone by. Now it is IR 5.0, and we have to know what is the difference between IR 4.0 and 5.0. IR 4.0 was mostly focusing on the not too much considering about the human contribution, but IR 5.0 is very much human centric, and we would like to have machine and human to work together in collaborative manner. So human machine collaboration is very important, and human judgment, creativity, values more are more central in IR 5.0. So there's a new terminology called cobot, which is known as also collaborative robotics. This is an era of IR 5.0. We use cobot instead of robot. So in cobot, robot and human will be working side by side without having any safety shield. Goal priority, we always talk about efficiency, speed, cost reduction, productivity in IR 4.0, but in IR 5.0, we are more into sustainability, environmental sustainability, social impact, and inclusive growth. And technology drivers are mostly data, connectivity, AI, and ML. AI means artificial intelligence, ML means machine learning for automation and industrial tech. Same technologies, but the we would like to see it in a different ways. Now the emphasis is more on human capacity building, capabilities, and caring for the environment. And challenges are in technical challenges, technical infrastructure, cost, skills, data, security, all these things for IR 4.0. However, the new challenges emerges for IR 5.0, which is balancing automation with human roles, ethical consideration, ensuring equitable access, and environmental constraints. So I hope that is all for today. Inshallah. Thank you very much. I hope you enjoyed the lecture. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.